Hello, this is Patrick Tanner, and I will be presenting to you on my discoveries on what determinants are and why they are related to their inverses. So, my initial question, very self-explanatory. It's the title of this PowerPoint. Why does the determinant determine if a matrix is invertible or not? Right? This is a question I had just randomly while I was on the determinant section in my linear algebra course. So let's say we have these two by two matrices, right? There is a 3303 and its determinant is 9. There's a 1111 and its determinant is 0. This is easily verifiable by the AD minus BC formula that we all know. And my first question is, wow, what is a determinant? Why did we get these numbers? You know, these numbers are kind of meaningless. Like, what is AD minus BC? What does it have to do with these funny numbers, right? And secondly, what is an inverse? All right, let's get into determinants. So here is my definition for determinant. It's really more of a geometric interpretation because it doesn't really account for negatives, but this is simple enough, I think. So the first step is to divide the square matrix into vectors. You can see here, I've divided them into column vectors, thinking that the first entry is x and the second entry is y. You then draw out their vectors, which will leave you with a square for this identity matrix. And, as you can see, the area of the parallelogram created by these vectors is a determinant of the 2 by 2 matrix. You can see here, 1 times 1 is equal to 1. And if you follow the diagonal rule for diagonal matrices, the determinant is just these multiplied, so it's just 1. All right, let's go through some more examples. So here is here's the first example that we have, right? The 3303. If we remember correctly, its determinant should be 9, but let's double check through our new way of visualizing, right? So, as we can see, the base is 3 units long, and its total height is also 3 units long, looking at its components. So, following base times height, its area is 9, and so that means, and that also agrees with the fact that its determinant is 9. All right, let's look at the second example that we had, 1111. And as we map these out, we can see that they map out to a straight line. And what is the area of a straight line? That's right, it's 0. All right, now let's generalize. Here we have a 3 by 3 matrix, and for 3 by 3 matrices, we're actually looking at the volume, right? Instead of the area, it's now volume of its parallelepiped. That's such a funny shape to say. But after some calculations, we get that its area is 18. All right. Now we will go into invertibility. So if the square matrix A is invertible, then AX equals to B has exactly one solution X for every vector B. This can be verified through looking at the equivalence statements in the elementary linear algebra book by Anton and Carl. Okay, so what does this mean though? All right, so this means that every input vector X is associated with one output vector B, and every output vector B is associated with one input vector X. If you guys have taken a discrete mathematics course, this can also be related to a bijection. So a bijection is just a function that says that every input value x is related to an output value, and the size of both of those sets of all the inputs and the sets of all the outputs, is the exact same. So everything gets mapped and nothing gets left over. All right. Now move on to matrix multiplications as transformations. All right. Now let's just get straight into the examples, since this is a very visual thing. All right, here we have a bunch of vectors on the left of it. Those are input vectors. They are all the red dots. And I have the matrices sort of mapped out in green over there, as if we were about to calculate the determinant. here we have the identity matrix, and we're going to multiply a bunch of these vectors onto the identity matrix. And as you can see here, our output vectors are the exact same, which is what we expect with the identity matrix. All right, let's get a little more complicated here. Here we have 1, 1, 0, 1. Okay, so we have the same input vectors, this red rectangle over here. But as you can see, as we changed our little green square down there, everything slanted with the geometric interpretation of your determinant. So as the determinant also became like shifted, as the vectors inside the determinant became shifted, the rectangle itself also shifts, as you can see by the blue parallelogram kind of outlined there. And obviously, multiplying those thingies, those previous outputs, by the inverse matrix, which is, just a -1 there because that's an elementary matrix, you can figure this transformation is called a shear transformation. That was just a little fun fact because we didn't really go over this in the class. All right, now we're going to look at the uninvertible matrices, right? This is the big one, right? This is the determinant equals 0. So supposedly it's uninvertible, and we should hopefully be able to realize why this is by looking at this, right? So we have our same red point input vectors, a funny little rectangle, and then we multiply it by our second example from the very, very beginning. And we get this straight line, right? And there is a big problem with this, as you can see, right? You guys remember when I went over invertibility, right? Every single point had its own vector associated with it, and every single vector had its own point associated with it. But as you can see here, six distinct vectors map to 4 vectors instead. And specifically, I'll show you an example of what vectors were lost somehow. So 2, 1, and 1, 2, when multiplied against 1, 1, 1, 1, both result in 3, 3. So after looking at this, I gotta ask you this. If an inverse were to exist for this matrix, would 3, 3 turn into 2, 1, or 1, 2? So if we were to reverse this transformation somehow, how would we know if 3, 3 would turn into either of these two things? And the answer is, you don't, okay? So looking at this, we can figure out and learn that matrices with determinant 0 squish vectors into a lower dimension, resulting in multiple vectors in the higher dimension, mapping to one vector in the lower dimension, which is a big problem. All right, now we get to go into the applications of this. Now we get to apply what we've learned about determinants and see how that works out with other things. Now we get into hill ciphers in cryptography. All right. So I'm not going to go too in depth into this since my group already covered hill ciphers on our collective video. But essentially, it's a cipher that combines matrix multiplication and mod arithmetic. So all it does, it converts your plaintext, your English plaintext, into numbers, divides those numbers into separate vectors, and then multiply those vectors by a key. And then that key is a square matrix, obviously. And out comes another vector, and then you turn that back into a letter after doing some modular arithmetic. And then you get some ciphertext that is pretty scrambled. And now let's go into choosing a key matrix. For a key matrix to be valid, it must be invertible. And its determinant mod n must be coprime with n, where n is the number of characters. But this is a linear algebra class. I'm not going to bore you with modular arithmetic, and we don't really need to go into it. Just assume that the condition for that part is always met. All right. Now we go in now we go into two different potential keys, right? Let's say we had this key, 3325, and this other key, 3624. My question is, which key is invalid and why? Okay, so now knowing about looking at what we know about determinants, um, the key on the right is not valid because its determinant is 0 and it is therefore invertible. Now let's think about this and why this doesn't work with by using the same logic we had with the 1111 graph, right? Let's say we had two different messages, right? And we wanted to, encode them using this cipher. And it turns out these two messages somehow end up being the exact same ciphertext, right? If we were somehow able to get a matrix that was the inverse of that, what would that ciphertext turn into? Would it turn into message number 1 or message number 2, right? Doesn't make any sense because that key just doesn't work out according to its determinant. And, yep, that's really about it. And we've reached the end of our PowerPoint here. Here are my citations. It is no longer informal. I've updated them with actual citations right there. So you can thank the elementary linear algebra textbook by Colin Anderson, the Desmos graphing calculator for all their visuals, Grant Sanderson for his little intro video on determinants, which is very, very helpful. I suggest you check out his linear algebra series on YouTube. So cool. And this random Wikipedia picture I found, uploaded by this user, that's where the tracking ends though. It was literally uploaded by this user, so I'm going to quote him for it. That's pretty much it for my slideshow. Thank you very much, and peace out.